Hello class, this is going to be your lecture on all things geodatabases. So starting off, we're just going to all start from the same footing and go over why are geodatabases called geodatabases. Well, the name is simply short for geographic database. That's where the name came from. It seems silly to call this a new data format, but it is the newest data format in the Esri world, but it is already 20 years old. So it's been around for 20 years. It is the most up-to-date format for storing spatial and attribute data. What a geodatabase is that it is a collection of your geographic data sets. Those can be your points, your lines, your polygons, and also your raster data. And it is held in a common file system folder, Microsoft Access database, or multi-user relational database. So a geodatabase is a single file that has the ability to hold multiple pieces of information. So what we're going to start off with here is going over the different types of geodatabases. There are three primary types of geodatabases: a personal geodatabase, a file geodatabase, and then what's called a multi-user or enterprise or ArcSDE geodatabase. So we're going to introduce all three of them here, and then we'll talk about each of them in detail in the slides to come. The personal geodatabase was the original geodatabase type. It was what came out in the year 2000. It was when ArcGIS and ArcMap 9.1 came out is when the personal geodatabase was released. It is still supported, but it is not necessarily recommended that you create these anymore. Next in generation is our file geodatabase. It came out around ArcGIS 9.2 and is still fully supported, and it is the type of geodatabase that we will be working with. The last one listed here, this multi-user or enterprise geodatabase, these are geodatabases that act very similar to file geodatabases. They're used by many organizations that have lots of GIS employees, people who all need to be accessing centralized data, but they also need to be able to do their own work, but the organization wants to keep one primary copy of that data. We will not be using these this semester, except for later in the lecture. I'll tell you the one place we'll get a preview of them. But the key here is that if you understand the logic of the file geodatabase structure, you will very easily be able to walk into an organization running an enterprise geodatabase system because you will understand the file structure. What you will learn is just simply how they are managing their database system behind the scenes that's storing the geodatabase as opposed to it being stored in a file in a Windows environment. All right, so our personal geodatabases, these were the first ones. These were first generation geodatabases. They were built off of Microsoft Access, so that's why you notice that they have that .mdb extension, the same as Access. So they did have some limitations, the first biggest one being that their size limit was 2 gigs. And they had that 2 gigabyte size limit because that's the size limit of a Microsoft Access file. And I just did some Googling the other day, and the most recent Office versions still have that same file limit on personal geodatabases. Personal geodatabases could be read by multiple users at the same time. Multiple people can look at the data. You could add the features, add the polygons from a personal geodatabase. Multiple people could, but they can only be edited by one person at a time. So only one person who's looking at the data will be able to edit it at a time. And with versions 9.1 and beyond, you could store both vector and raster data, but it's converting all of your raster data to IMG files in order to store inside of that .mdb file. So the big thing here was that 2 gig size limit. Because of that, the processes and the properties for setting up a personal geodatabase were very prescriptive. We had to make sure that we were doing things so that we were the most efficient in the use of those 2 gigabytes. So I'll highlight as we go and talk through how we build a file geodatabase in our exercises, and I'll highlight the places where now you simply see one wizard screen and hit next, whereas with the personal geodatabase, you would spend several hours trying to figure out how to set up the settings to maximize your spatial area and minimize the amount of space that you're taking up. So that's the personal geodatabase. After that, about ArcGIS 9.2, we got the file geodatabase. very similar to personal geodatabases in that multiple users can read the files. However, only one user can edit at a time. They can also store raster data, and actually over time you'll notice that the list of raster data sets, raster file types that can be stored within a file geodatabase, that list gets longer. So they're very adaptable. They're building them and changing the file geodatabase format in such a way that it can store different types of raster data. The biggest difference is that it's not built on a Microsoft Access database. So you'll notice that it has an extension of a .gdb, which stands for Geodatabase. It is an open file system. It's not limited to the Microsoft Access 2 gigs. In theory, a file geodatabase has a 1 terabyte size limit. However, if you were to try and use a file geodatabase that's a terabyte within a desktop environment, the desktop software itself would probably choke on that data because you wouldn't have enough memory in your computer to deal with it. But in theory, they can basically be as big as you want them to be. The last type we're going to talk about are these enterprise geodatabases. The first thing listed here is the biggest difference. They can be read and edited by multiple users at the same time. The process that does this is something we call versioning or distributed editing. So these enterprise and multi-user geodatabases aren't just stored on your desktop and accessed through your desktop GIS. The data itself is stored in a relational database system that is separate from your GIS installation. So Oracle, SQL Server, DB2, that's the structure that holds your enterprise geodatabase. That is then connected to your enterprise GIS licensing. And then what happens is that individuals can check out their own copies of the centralized data living in those servers on those database management systems. They check out a copy, do their work on that copy, and then they check that data back in. So essentially what they're doing is they're pulling out a version of the data. They're doing their own editing, so multiple people could pull out their own version, do their own editing, which would be the distributed editing, right? It's distributed amongst multiple people. And then at the end of the operation or at the end of the day, they go through a process that they check their data back in. And then the database operates off of a set of rules associated with that data and associated with those users to then update the centralized data set with the edits that were done by the distributed editors. Now, some of the rules that live along with this is that each individual user would have certain rules associated with them about maybe the spatial area that they had authorization to edit, or the particular data sets that they had authorization to edit. You could even have decision rules on people could be in a hierarchy within your organization. And the manager, if two people, let's say two people, Sue and Sally, check out the same pieces of data on one day. And they do editing on each of their data sets, but some of the places where they edit, it overlaps. So they've both made edits, and they go to check back in at the end of the day. Well, the database needs to figure out, it can't take both of their edits in the same area because that doesn't make sense. It needs to have a decision rule in the system about which edits does it take. That is driven by the hierarchy in the organization of Sue and Sally. So let's say Sue is the GIS manager and Sally is the GIS specialist. Well, if you set the GIS manager role to be higher than the specialist role, the database knows that if there's any overlapping edits between Sue and Sally, the GIS manager's edits should override the GIS specialist edits. So that's how organizations deal with a lot of this GIS data that needs to be in a centralized system. And a lot of these organizations, it's not the GIS staff that's managing these systems. If it is, it's somebody who has been hired specifically for this to be a large portion of their job. So this type of database management is not something we necessarily teach in this class, but if you were to walk into an organization that has this type of system, you could very easily be an end user, and with some training on whichever database management system they have, you could also roll into a position that you could be somebody who is in charge of the rules and of this organization within their overall multi-user geodatabase. Oh, but I did say that I would also give you a heads up that we will get to see this play out a little bit. So later on in the semester, we're going to do mobile data collection. And to do that, we're going to use Esri's Collector app. And what we do there is that we build geodatabases with a certain set of specifics and properties. We publish them to our cloud organization, and then we have access to them on our mobile devices. And we are going to go out and collect GPS data, and we're going to store it inside of an existing geodatabase. In order to do that, each of us with a device, if we're all out collecting data for the same project, we all have to be able to collect our own data. We are all working with a version of that geodatabase that we pulled out of the cloud. And then what we do at the end of the day is that we want to sync our data back to the organization so that that data gets stored in the organization. And that's us checking our data back in. So when we get to that portion of class, I'll remind you of that. But don't walk away from this thinking that you won't get any experience with this enterprise system, because when we do the Collector app, mobile data collection, you'll get to see the concepts of pulling data out of a centralized managed system and then checking it back in. All right, so I've talked about 3. So now which type do you choose? Well, the personal geodatabase, for the first 10 years, that's basically what everybody was creating. And at this time, shapefiles were still being created en masse as well. Esri was hoping when they created the file geodatabase that most people would migrate there, and that actually has happened, because working with the file geodatabase, its size and just its ease of creation is so much better than the personal geodatabase. So you really don't see those created anymore. You might find some of them out on the internet that people are serving to download, or if there's an organization that's just how they work, you might have to create it there. And if you're working with a version of ArcMap of 9.1 or earlier, they do still exist out there. You would have to do a personal geodatabase, because that software did not even know that the file geodatabase was coming, and it's not programmed to be able to work with it. File geodatabases, this is the current one. This is one that I don't even know. You can actually create a personal geodatabase in ArcPro, but file geodatabase, you'll notice, is the one that's highlighted. It's easier to create and manage, no limits, and it technically is not tied to an operating system because it's an open file system. However, the Esri desktop products are tied to Windows, so that's kind of it's good, but then again, if you're an Esri customer, it really doesn't matter. So that's going to be the one you would choose. We just talked about some of those scenarios where you would use an enterprise system, and really your only option for doing that is if there's an enterprise system built for you to work within. So for the most part, you're going to choose a file geodatabase. So there's all the types, but why did we move to this new data model, right? We'd had coverages, then we had shape files, then they created this geodatabase. So why did they do that? Well, for 3 main reasons. The first listed there is that it allows you to group data into a centrally managed package. So instead of having folders of lists of shapefiles or shapefiles spread out all over the place, it allows you to create a centralized package for either an area or a project, and then all of the data lives inside of that. Really important, it brought back this concept of interactive relationships, which is our topology. It allowed for us to create data that's either topologically correct, that harkens back to the coverage data model, that mathematical topology, or it allows for us to take advantage of relationships between data sets or within a data set that we know should exist. So for example, if you have in your file geodatabase a data set of roads and a data set of bus routes, well, it makes sense that all of your bus routes should be in the exact same place as some of your roads, right? Because your bus routes are built off roads. Well, if you have a geodatabase, a file geodatabase, you can build a topology that checks for that. And you can build a topology rule that says all of my bus routes have to be coincident, have to share space with my roads. And if they don't, it's going to flag your bus routes that don't overlap with roads. So it allowed for us to be able to model interactive relationships. And that topology topic is the next topic we'll talk about after we get through all of our geodatabase introductions. The last here is efficient use of space. So especially in this world of big data right now and big data sets, the geodatabase, if you look at the file size of a data set stored in a coverage, stored in a shapefile versus stored in a file geodatabase, you will see that the file size dramatically decreases as you get to the file geodatabase. So when the file geodatabase was being developed at the end of the last century for deployment in the early 2000s, we weren't at a time where you could have a terabyte on your desk. It just didn't happen, and if it did, it was like tens of thousands of dollars to have that much storage space. Right now, I could have a terabyte on a thumb drive, and pay $50 for it from the bookstore. But that wasn't the case when this database structure was developed. Our hard drive space was still very limited and very expensive. So the geodatabase was a way to build data in such a way that it would minimize the amount of space that it took on disk. That also allows for us to view and edit faster. So the smaller the data size, even though we have a terabyte available very easily for us, the smaller our data, the easier it is for any type of software to use it. So it still becomes a benefit for us today. All right, so the geodatabase model is fundamentally different than the data models coming before it, the coverage data model and the shapefile data model. So in this section of the lecture, we're going to go over and introduce the object-based data model. But as a review, I want us to remind ourselves that the data model for coverages and shapefiles was called the georelational data model. And remember, that was the model where your spatial data and your attribute data are stored separately in separate files in a split system. And the way that the data works is it has to synchronize between those two components. So there's data synchronization. So a mini relational database structure is happening in there in order to get your spatial data and your tabular data to synchronize. Now, introduce the object-based data model. So our object-based data model, our geodatabases, are based upon object-oriented technology, or what's called object-oriented programming. So you guys are completely familiar with this concept. In the Windows environment, even on the Mac side, anything that's a window, anything that has icons on to click on, that's what object-oriented technology is. So instead of opening up a command line and typing in your instructions, so when I first started using computers, you had to go to the command line and say, open WinWord, and an Office software for typing would open up. Now you double click on an icon, or you go to a menu and you select that word and you click on that word. So the icon and the word listed there are objects. You're clicking on these objects, and the objects know what to do when you click on them. Okay, so that's the underpinning of object-oriented technology. You're working with objects, you're not typing out command lines, and these objects know what is allowed to be done with them because of the way the software that you're working with has been programmed. So let's talk about exactly what an object is. Objects are just things, and they have a state and a behavior. And in the terms of programming, we talk about those states as properties and those behaviors as methods. So let's walk through an example of an object that would have some properties and some methods associated with it, a really common object. So your car, okay? So your car is an object. It's a thing you can go out and touch. It has a set of properties. It has the color of your car, the manufacturer, your license plate number, I don't know, the number of doors you have. Do you have air conditioning? Does it have a sunroof? All of those properties, the things that describe its state, what it looks like. Then you have methods. The methods are what can be done with that object. So it's doing something. It's a function or a procedure. And with our car, the different methods, what can your car do? Well, your car can move forward. It can move backward. It can stop. The air conditioning can be turned on. It can be turned off. The radio can be turned on, it can be turned off. So all of the things, the behaviors, those things that can be done are the methods. So objects are things that have states and behaviors, which we talk about as properties and methods. So let's transition that over to GIS a little bit. So most of what we're going to interact with in GIS are actual objects. So our points are objects, lines, polygons, tables. A table record is an object. Each of these objects has a set of properties, things that describe them, and a set of methods. And those are the things that are doing. That's like the verbs. So the properties are like your adjectives, and the methods are your verbs. So you're describing it, and then you're trying to do something with it. So if we look at this, and we look at this from the point of view of a polygon being an object, an example of some properties of that polygon is the area, the number of vertices that are made up around the outer circle of its perimeter, some methods that can be done. What can you do to a polygon? Where you can delete the polygon, you can edit the polygon, you could add another polygon, or you could add some vertices, or you could delete those vertices. Or you could reshape your polygon. All of those tools that you can do something with, those are methods that are associated with that particular object and its properties. So let's talk about this and get a little view of your data within a GIS. So let's talk about this specific to our spatial features as being an object. So with object-based data model, with our geodatabase, it's going to treat all of our spatial data as objects. So now we know, okay, if it's an object, it means it has properties and methods. So an object could be a spatial feature, such as a polygon within this data set of parcels. So this parcel that you see outlined in cyan. The geometry of the parcel is stored as an attribute in the table. So that's one of the things about object-based programming, is that things are stored as attributes of the object. So one of the attributes of the object is the actual shape. Is it a point, a line, or a polygon? That's why you see that shape field in a geodatabase. So this concept eliminates that need for data synchronization, because the actual physical shape, the geometry of the object, is stored as an attribute in the table. All right, so all of that allows for our spatial features, our objects, to be associated with a set of properties and methods. So the property, again, describes an attribute or the characteristic of the object. The method is what's being done. So down there at the bottom, I summarize that. Your object could be your parcel. The property of your parcel could be the shape, the extent, and the method, one of the methods available to that. So there would be multiple methods available for that property, but one method available is just the fact that you could delete it, right? So that's one method, that's one thing, that's one action that could be done to that particular object of parcel. All right, so these two sentences summarize this up for us. So working with an object-based GIS, which is what the geodatabase model is dictated by the properties and methods that have been defined for the objects within that GIS. So let's boil that down to our method, property, and object terminology that we've been working with. What you can do with a data set and its attributes is limited, and I would say driven, by how your GIS, specific for us, ArcGIS, has been programmed. So the methods available to work with an object and its properties have been defined by the software vendor and defined by convention of the field and how data is supposed to be worked with, all right? So all of these methods are tied to our properties and tied to our objects. And in the world of GIS, we think of these things as tools. We think of these things as right-click properties, and we think of these things as points, lines, and polygons. All right, so now that we understand what the geodatabase model is, the underpinnings of it, and how it's different fundamentally from our previous types of data, now we're going to talk about the contents and properties of our geodatabases. So what can be stored inside of a geodatabase? You can have feature classes, which are your points, lines, and your polygons. You can have things called featured data sets. And a featured data set can be thought of as a subfolder within your geodatabase. It's not a physical feature itself. It's not a GIS data set. It's a subfolder within your geodatabase that allows you to have a collection of feature classes. In that feature data set, everything that's stored within there has to have the same spatial reference. And it's within the feature data set, when we move into topology, that you'll see that the topology of your geodatabase plays out within the feature data set. You can also have standalone tables in a geodatabase, that type of non-spatial data. You can have raster data sets in the file geodatabase model. The list of raster file types that are supported is a laundry list. I don't have them all listed here, but chances are any raster format that you have are going to be able to be included in your file geodatabase. All right, so all of those things inside of a geodatabase we're going to talk about specifically. So what is a geodatabase feature class? It is a collection of geographic features with the same geometry type. a point, a line, a polygon. In the geodatabase model, that also includes annotations. So annotations are not new. They've actually existed since the coverage data model. An annotation is effectively a smart label. It is a label that stands apart from your data that has an XY coordinate. So instead of just turning on labels for, say, your polygons, if you generate annotations for them, the annotation becomes its own feature class inside of the geodatabase, and you can actually move it around and edit it. There are things called dimensions, which are a special annotation type, multi-points, which when we get into LiDAR at the end of the semester, we'll talk about multi-points, but it's a way to take a big data set that has millions and sometimes billions of points, and the geodatabase can consume that and turn it into a multi-point data set, meaning it's not going to store a record for all of the billions of points. It's going to work at condensing some of that down so that your computer and the data model can handle it. And the same for concept for multi-patches, and that's for 3D representations of data. If there's hundreds, thousands of millions of them, these multi-patches can be created, and it's just a way for the software to be able to better deal with big data. So a feature class can either stand alone within a geodatabase. So we started hearing the word feature class when geodatabases came out, but a feature class has been around for a long time. It can either stand alone in your geodatabase, or it can be contained within a shapefile. So you have shapefile feature classes. But a shapefile can only hold one feature class, a point, a line, or a polygon. They can also be contained within coverages. And remember, coverages could hold multiple feature types. You could have a polygon feature class and a line feature class inside of the same coverage. Or your feature classes can be within a geodatabase feature data set. So this feature class term, don't let it confuse you. It is synonymous with point, line, and polygon. That's what a feature class is. The properties associated with a geodatabase feature class are these two things in orange here, your XY tolerance and your XY resolution. This is actually where the process for creating a geodatabase and the file geodatabase model versus the personal geodatabase model diverge greatly. This is one of those things where we used to spend the better part of a class period hand calculating what these numbers should be so that we could most efficiently store data within a personal geodatabase. We no longer do that. I'm going to talk to you about what these two numbers are, and you're going to be required to remember and respond to what these numbers are. However, we're going to go ahead and take the defaults that are generated by the software, and those are going to be appropriate for our purposes in class, and 9 times out of 10, they're going to be appropriate for what you do outside of class as well. All right, so let's go through the definition of each of these. The XY tolerance is what is used to set the minimum distance between coordinates. So this is the minimum distance between your vertices in a line or a polygon, the minimum distance between lines in a data set, between polygons, between points. It's the minimum distance between something before it is considered to be coincident. So it's the closest that two features or two things can get in your GIS and in your data set before it effectively just gets merged together, and the software assumes that these two things were meant to be in the exact same place and represent one object. So your tools use this tolerance value to determine the minimum distance between separating of features, and it also is what's used to consider coincident, whether or not they are sharing space or not. This distance is actually very, very small. So it is set to be 0.0001 meters in distance. So think about how small of a distance that is. And I actually give it to you in feet, or the data set projection equivalent. So if your data is in state plane, Ohio feet, this is the minimum distance. I mean, that is so sub-foot. You would have to zoom in so far in order to see it. And then that's what it is in decimal degrees, although we wouldn't want to set up any type of topology with data set that's in geographic and looking at things in degrees. But that gives you a concept of how small that distance is. So if you ever need to change this, chances are you would make the distance to be bigger. If you do need to go through and clean up or find places where you have some dirty data where things were meant to be the same thing, they got digitized slightly off and you need to try and find them, that's where you can start to go in and adjust that tolerance. All right, so that's XY tolerance. How close can things be before they're considered coincident? Then there's XY resolution, and this is your numeric precision used to store your XY coordinate values. It's the number of significant digits past the decimal that are used to store your location. So the default that you see there again is if you're in UTM or Albers and you're in meters, it's 0.0001 meters. It's the default in the software, and we're going to go ahead and keep that XY resolution as well. It's maximized in the software for whatever coordinate system you're using. So when we go through the wizards, we're going to keep the defaults, but you need to be able to tell me the difference between what XY tolerance and XY resolution are. All right, so why was this all done? This was all done to minimize disk space, but like I said, it's not as necessary as it was with the personal geodatabase model, so we don't have to do any hand calculations anymore. So we're just going to take what the computer says for us, what the software says. And as I mentioned, the default value is going to be appropriate for class and for most real-world experiences. All right, so that moves us on to the feature data set. The feature data set is a collection of feature classes that share the same spatial reference. And the feature data set is actually a thing. It's a subfolder. You can't interact with it within the map view, but it actually can store data. So the feature data set was developed for two primary reasons. The first being simply to be able to thematically organize your data. If you have lots of data in a study area or lots of data in a geodatabase, sometimes it's nice to be able to bin them into subfolders. The most important reason, however, is that it allows us to take advantage of spatial relationships through topology. One of the reasons why the feature data set is the only place for topology is because the data in a feature data set has to share the same spatial reference, and that is enforced in the software. Your geodatabase overall doesn't have to have data of the same coordinate system. You could have 5 different data sets in 5 different coordinate systems or in 5 different areas of the world. That's fine. The geodatabase doesn't care. Now, whether or not that makes sense for your data, that's for you, the GIS professional, to figure out. A lot of times your data might be in the same coordinate system in a geodatabase, especially if it's for the same physical area. But most definitely within your feature data set, everything has to be in the same coordinate system. All right, so that spatial reference, how is that defined and how is that enforced within the data model? So it's defined by the person who creates the feature data set. In that creation process, you choose the projection in all of the X, Y, Z, and M tolerances. We'll talk about those in the exercise. However, anything else, any feature classes that either get created within that feature data set or get moved to that feature data set, the spatial reference is enforced through spatial reference inheritance. So any feature class created within an existing feature data set will automatically inherit the spatial reference from that feature data set. And we'll go through an exercise that makes that very clear. When you create a feature class just at the geodatabase level, you have to hit a screen and make some choices about the spatial reference for that data set. If you start that feature class creation process, however, from the feature data set level by right-clicking on your feature data set instead, you will notice that that screen doesn't exist in the wizard to create your feature class if you start there, because it's going to automatically inherit the spatial reference that exists for the feature data set. So where do file geodatabases get created? They get created like shapefiles in the catalog window. There's also a geoprocessing tool that you can open for creation of new file geodatabases. But most often you just go to catalog, you right click, say new file geodatabase, and then it's automatically added there, and you can rename it and start to build it from the catalog view. So once you have it, it's just empty. The geodatabase itself is just a container. It's not the data, so you have to populate it. There are 2 ways you can populate a geodatabase. You can import existing data. That data can be from a coverage, from a shapefile, from another geodatabase. So you can move existing data and you can either migrate it to the new data model or just move it from another geodatabase, or you can start the data creation process from within that geodatabase and right click on the geodatabase and do new feature class or new table or new feature data set. All of those things, both the importing and the creating new, we will do in our exercise after this lecture. All right, once we have data in there, we have some ways within the geodatabase model to manage for data entry. So in red there I have, imagine all of the problems that can occur when humans are manually entering data. from things that are capitalized versus not capitalized, from the spelling of words, like the spelling of the word canceling. Does it have 2 L's? Does it have 1 L? All of those different things that can happen, especially when you're in the field, when you're dealing with humans. Sometimes consistency is hard, but it's that consistency that we rely on in order to run queries to be able to summarize our data. So one of the things that's really great about the geodatabase model is that it gives us this concept of drop-down menus for fields that we can set up. These drop-down menus are called and function off of domains. So a domain is a very database-centric topic. So if you've had a database class, this concept of domains should not be new. But a table domain is what allows you to interact with a predefined list of options. So think about any form you've filled out, and it had a drop-down list as opposed to a place to type in. Those drop-down lists are just domains. It's a predefined list of the options that you have. So this is a really important part of the geodatabase building process that ties directly into our mobile data collection, because when you have people out in the field, as much as possible, you want to give them these drop-down lists so your data collection is as consistent as possible. So that's here in the example on our table, we have a field called rating, and you can see there that they've clicked in that field, and there's the options that they have available to them. And those options have just been coded by the GIS person who built the database and set up the properties. So domains are typically created at the geodatabase level, although you'll see in Pro that there's another creation place to create them by viewing at the feature class level, but I still want you to understand that no matter where you create them, they live at the geodatabase level. As soon as you create a domain, they are available to all of the feature classes within your geodatabase. So that's why we talk about them created and stored at the geodatabase level, and they are implemented at the feature class level. That's where you'll use them. So as long as the domain is in your geodatabase, you have access to it for a feature class. They are an option for any table field. However, a domain actually has a type. So you're going to set up the domain to either connect up with a text field or a numeric field or a date field. That means that that domain can only be used on fields that are a text field, a date field, or a numeric field. So the type of the domain has to match the type of the field. And your domains rely upon what's called coded values, and the code is what the table editor will see, but the code doesn't need to be a number. The code can actually be the same as what gets stored in the database, or the code could be a numeric number, but what the user sees is text that describes that number. So regardless, the drop-down list is what the person will see, and then the person who set up the domain drives what gets stored in the database in the background, whether it's just a duplicate of what the person sees in the drop-down list, or if the drop-down list is actually a description of a coded value that gets stored in the database. All right, the last thing we're going to talk about in our geodatabases is this concept of attachments. So a few years ago, this concept was created for file geodatabases as a way to attach non-GIS data to our individual features, features within our feature classes. So attachments attach themselves to individual feature records. These can be photos, these can be Word documents, these can be PDFs, these could be floor plans. Anything you can think of, basically any file type, you could attach to individual features in your geodatabase. So this makes it really nice if you're out in the field and you're taking pictures. You can set up your geodatabase to automatically store those pictures that you take while you're in data collection mode, to have it stored as an attachment to that record, so that when you come back into the office and you click on the field point, it pulls up not only all of the attributes of that field, but it also pulls up the attachment or the picture. Excuse me. So right now we have kind of a dual thought process on how to store ancillary attachment-like data in the world of GIS. You can either use these attachments, which physically pull in those files and store them as a part of your geodatabase. So these pictures that you're seeing on the screen are stored as a part of the geodatabase. They live in the geodatabase. Same would be for a Word document. It will get converted and stored inside, or a PDF. Excuse me. You have that methodology, or you have the more traditional methodology of these things that you want to view as attachments or ancillary data get stored on a separate server, or they get stored on the web. So the way we used to connect up to all of our pictures was pictures were stored in a centralized location on a web page or in a Flickr account, and then you would attach to them by putting in the URL to the picture in the attribute table. You would have a field for the URL, and then you would select that and turn that into a hyperlink so that when you looked at your data, you could click on that hyperlink and see that ancillary piece of information. You could store anything on the internet and then connect to it up that way by knowing its address on the internet. So you have that way of storing things and accessing them via hyperlinks, or you have the attachment model. They both have their pros and cons. The pros of your attachments are that it's in your data. You don't have to connect up to another separate server. You don't have to have a Flickr account. You don't have to worry about an internet connection or somebody changing something on the, on where your data is served, or moving things or changing the URL. It's all there inside of your data. Kind of the con of that is that if your attachments are things that need to change over time. So if the pictures, like if they're properties, so if you're an auditor and it's, you're putting in property pictures for every year, and you go out to do an assessment of a property, and every year you're required to take pictures and update those pictures in the records. Well, going through and having to update that in an attachment base probably is going to be a longer workload for updating all of those pictures. Then maybe storing those all in a Flickr site and keeping the URL, the path name to all of those pictures effectively the same. Then you just replace the picture, but the address to it stays the same, and you don't have to do anything except for replace the images where they live. So there are definitely pros and cons of both methods. Organizations tend to use both of them, but understand that attachments are going to go into your geodatabase. They live in your geodatabase, and we will play with attachments when we do our mobile data collection. All right, the last thing we're going to talk about here when it comes to terminology is this concept of schema. You will see schema all over the place when you're in the Esri documentation. Schema is just a really fancy term for all of the properties you set up for your geodatabase. So if your geodatabase has domains, that's part of the geodatabase schema. If your geodatabase has featured data sets, that's part of its schema. So basically anything you set up in your geodatabase is just the schema of the database. So when you hear that term, don't be thrown, and just know that it's just the term for what a geodatabase is and how it's set up. All right, so what do you need to address before building a geodatabase? You need to address what kind of data will you be storing? What projection do you want it to be in? How do you want you to organize your data? Will it need to contain topology? Do you need to manage data entry? Do you need to attach non-GIS files? Will the geodatabase be used by multiple people, viewed by multiple people, edited by multiple people? What's your organizational structure when it comes to an enterprise system? So those are all questions that you need to ask before you build your geodatabase, and it's going to lead you to choose the proper geodatabase type and the proper properties within your geodatabase. All right, the very, very last thing is that I just want to revisit field data types specific to geodatabases. In ArcGIS, there are three primary field data types: numeric, text, also called string, and date. Within the geodatabase, the numeric type falls within four categories: short integer, long integer, floating point, and double precision floating point. Short integer, it's an integer, no decimals, 5 significant digits. Long integer, still no decimals, but up to 10 significant digits. Floating point, also called floats, stores a decimal point, and it can float anywhere in that 7 significant digits. So you could have 1.6666777, right? So you'd have 7 numbers, but that point could be after the first digit, or it could be all the way at the end. Double precision floating point is that same concept, also called doubles, but you have up to 15 significant digits. I highly recommend when you're building data, if you need an integer field, go ahead and make it long integer. And if you need a floating point, a decimal field, go ahead and make it the double precision or the double. That just gives you the biggest number of digits in case you get into data that needs it. Because once this field is set, you cannot change that value. And if you start to do data calculations that go beyond those significant digits, the software is not going to tell you. You're not going to get a message saying you're creating a number bigger than what can fit in that field. It's just going to start to cut numbers off. So it's always best to go with the larger number. There are some other geodatabase field types. The OID, which is your object identifier, which is synonymous to the FID from the shapefile data model, that feature identifier that's automatically created by the software. It's its internal way to keep track of the unique records. There's also the global identifier. It's also automatically added. Software developers, if you go into that field, take advantage of that global identifier often. So for all of the data in your organization, everything would have a unique code. The geometry field, you'll see that shape field. It just stores the geometry type. Also automatically added. There's also a field type that can be a blob. It stores data as binary, but that needs a third-party extension to actually access and view, and we won't be doing anything with blobs, but you'll see them. So I wanted you to see that, they're there. We just aren't going to be working with them. All right, that was a long 45 minutes. So hopefully you can take a breath, take a deep breath, relax a little bit, and then the activity that you're going to do is going to go in and explore an existing geodatabase, and then the bulk of it's going to be building and populating your own geodatabase, taking advantage of all the things we just talked about, but putting it into an actual geodatabase and creating data and migrating data and seeing how these geodatabases get built so that we can take advantage of them and get into topology in the next week, and then moving after that, take advantage of those geodatabases for our mobile data collection. All right, I hope you guys have a fun time with the exercise, and I'm sure I'll see you soon.